This is FE Peer Review. The date is April the 27th, 2021. This video is in response to one just put out by Gary Wybenga in which he's looking at Polaris measurements. This is a screenshot from Gary's video. We see that he has nicely and very carefully drawn out this little diagram that shows across the bottom 10-degree increments of latitude and the angle at which the view of Polaris changes. I'm starting this video response by essentially recreating his drawing. I'm using SketchUp. It's a fairly sophisticated 3D graphics tool, but I'm using it in a very simple 2D mode here so that it's just a sketching tool, 2D, nothing fancy about it, no CGI. And I'm using it because it's precise and easy to zoom in and out, and I can put things on different layers, which means I can turn stuff on and off, and it's a little easier to see things. So what I did was I drew a vertical line, which would be equivalent to the line. It's right here. It's not showing up very well. So what I did was I drew a vertical line at the far left. You can see it right here. See it right there, which is equivalent to the vertical line at the far left of Gary's drawing. And then I drew a series of shorter lines, equally spaced at the bottom, equally spaced across the bottom, and we'll confirm that in a moment. And each one of equal length, which we'll confirm. And then I rotated each one 10 degrees, 20 degrees, 30 degrees, and so forth. So I'm going to come in a little closer so you can see it a little better and turn on a few. That shows the dimensions. I drew the line as a 10-meter line. You can see that each one is 10 meters long, and they're each one 10 meters apart. There's actually a 10-meter long line down here that's been rotated 90 degrees. Kind of hard to see, but it's there. And the dimensions are put in by SketchUp. I don't write the number 10 meters. When I draw the line, I tell SketchUp to make a 10-meter line, and then when I use the dimension tool and put in the dimension arrow, SketchUp fills in the 10-meter. Another thing I did was to put in dashed lines that are continuations to show where they intersect that left line at the left. And then the last thing I did here, or not the last, but the next thing I did was vertical dimensions. Again, using the dimension tool from SketchUp, I dimensioned all this. Now, I didn't do a single bit of math in any of this. I didn't calculate anything to get these numbers. These numbers were determined by SketchUp based on my graphic input. Last thing I'm going to show you here, and I'm going to turn these dimensions off, is a little protractor that I made, just like a screen version of the protractor you would have had when you were a kid at school, except I just stopped it at 90 degrees. Usually they're a half circle, 180 degrees. And it's got 10-degree marks that are the long lines, 5-degree marks, short lines on the outside, and 1-degree marks, short lines on the inside. And I put that in there just to show that these long lines, that these 10-meter long lines are indeed rotated by 10 degrees each. There you see the 80-degree mark, the 70-degree mark, the 60, and so forth, down to 10 degrees. And then finally the last one is 0, so I didn't bother putting it. That's just to show graphically that I have drawn this correctly. It's an interesting bit of geometry, but clearly it does not provide the answer as to where Polaris is actually located, specifically how far away it is from Earth. I'm working on the assumption here that Polaris is a real physical object at a single location in space. So this diagram, in that case, this diagram does not tell us where it is. And in fact, the observations that this diagram represents, the real physical observation this diagram represents, does not tell us where Polaris is, if this diagram is correctly representing our observation. So I'm going to move this next step of the discussion away from the Polaris thing and these extreme long distances that we're talking about, 690 miles for each step, I'm going to move it away from that scale and down to a smaller scale and simply look at perspective. What we are going to look at is that we have equal increments horizontally, 10 meters. But this diagram shows that the heights are different. The height is not changing the same amount with each equal step away. We're going to look at that next. Okay, let's look at the next step here and see what direction this is leading us in. What I've done is I've drawn a new diagram. It's next to the old one. I'll show you both side by side. There's the old diagram on the left and the new diagram on the right. And I'll explain a little bit here. What I did when I drew my new diagram was I took that first sloped view, which was the 80 degrees from the vertical, or 10 degrees down from the vertical, and it intersected it at a point up at the top. And I just arbitrarily picked that as a length that I'm going to use for the new diagram. So with this diagram, what that means is that this first solid line here is continued as a dashed line, and that's identical to our original diagram. And then I've made these little short solid lines down at the bottom to indicate the locations of our equal spacing away from the origin point. So these are equally spaced. And I've left in the original sloped, let's see if I can bring them up here, the original 10-meter lines that angled down 10 degrees each time. Now what happens if we say that from each of these station points, from each of these locations, some people are looking at an object in a fixed location in space. So this is an orthographic view. There's no perspective here. There's a person standing here, and a straight line connecting that person to that object has a certain angle. A straight line connecting this viewpoint to this object has a certain angle, and the same here. A straight line connecting this fixed viewpoint to that object has a certain angle. These are triangles. This is all this is, triangles. So what you'll see is that these dashed lines are diverging from the lines of our original diagram. The original lines from the diagram are dropping more quickly, and these dashed lines looking at a fixed location in space are not dropping as quickly. In fact, it's quite extreme. I saved it. I didn't draw them all in yet. I wanted to draw a few. So I made tick marks. That's 100 meters. From the vertical line at the left to the last tick mark is 100 meters. So I made another set of tick marks every 100 meters for another 500 meters. And I'm going to draw in the angles. So I've got a line going from this mark to the tip, and then back to here, and another one, and another one, and that'll be the last one for these purposes. So you can see that even when we've gone as far out as six times 600 meters, we've got this definite angle of view here. We have not gone down to zero. How far do we have to go to get this view to go to zero? If we're looking at it in terms of pure geometry, and we use geometry or trigonometry to find the answer, I'm only talking about triangles here. I'm not talking about space and perspective. If we are just simply looking at triangles, the answer as to how far out we have to go to get that angle to go to zero is infinity, and mathematical proofs are easily available. So that's what happens with triangles, trigonometry, when you try to use pure geometry to push that angle to zero. Okay, before moving to the next step here, I realized there is one more little thing about this diagram that I wanted to cover. And so what I've done is I've copied my little protractors onto the diagram so that we can quantify what the difference is between these dashed lines of this diagram with the original view lines from the first diagram. So starting at that 80-degree mark, we see that they both align because that was the basis of how I drew this diagram. Everything lines up. Let's moving over to the next one. We've got the dashed line diverging by a little less than a degree from the 70 mark. And then we get to the 60 and we're at 62 in a little bit. And then instead of 50, we've got almost 55 degrees. Instead of 40, we've got 48 and a half roughly. Instead of 30, we're up to 43 and a half. As you can see, the divergence is growing with each step. From 20, we're now at 40. And from 10, we're all the way up to 35 and a half roughly. So that allows us to put numbers. This is where it gets important and useful. That divergence, the difference between those, is allowing us to quantify why these two the difference in these two diagrams. I think that's key to the next step. Gary, it's clear to me from what you've said in comments on your video that you accept that Polaris is not at multiple locations in space and that there is an aspect of perspective which explains what is physically observed when viewing Polaris from different latitudes. These are some of the comments that you left. It isn't multiple heights. I'm assuming you mean from that then, I'm assuming you agree that Polaris is at a single location in space somewhere. Let me know if you don't agree with that. And then you add its perspective, which is how they set the latitudes. You do know things that are above you appear lower as they move away from you. It's no different than walking away from a telephone pole, and it's linear, which means it will become lower at a steady rate. And then you mentioned telephone poles as an example in a couple of other comments. It's 690 miles. It's linear, just like a line of telephone poles that are equally spaced apart. And then this Michael Dunleavy did some math, and you replied with, that's because you took all perspective out. That's the next thing I want to talk about here. And I think this is kind of a challenge you've put in front of yourself and us. And that is that you're claiming here that the straight math, the simple triangles, is not the complete solution in a sense, that there is some kind of perspective element that has to be incorporated with this triangles that will give a solution. Now, there's a question I have here. Do you believe that there is a quantifiable method of some kind that would enable us to locate a physical object in space, such as Polaris, based on measurements from what we see? Now, if that includes some aspect of perspective, I'm fine with that. If you think that's what it requires, but if you think, what I really want to know is, do you think there is a quantifiable method? I wrote it out as a problem statement. Is there a quantifiable way of determining from direct observations the location of the object in space? Do you think there is or is not? That's my first question to you. Do you think there is or is not? If you think there is a quantifiable method and that it involves perspective, do you know that method? Do you have it? Can you show us with math, including perspective, where the object is in space based on physical observations? Can you show us your process and your method for determining that? I'm asking you to show us. Please show us what this method is, if you have it. If you do not have it, please tell us you do not have it. And then, if you're going to claim such a method exists, tell us how you intend to determine what that method is and what your plan is for developing that method. If such a quantifiable method exists, do you know this method and will you share it with us? And if you believe such a method exists but do not yet know what it is, what is your plan for determining this method? I'm going back to this SketchUp model here because if you're in the category 4 there, where you believe such a quantified method does exist but you do not yet know what that method is and you plan to try to figure it out, these two diagrams that I developed, the first one based on yours and the second one I developed my own, they might be really useful to you because they contain numbers. It should be possible, I believe it should be possible to take these two diagrams and compare them and look at, in particular, I'll zoom in on this one over here, how the angles vary more and more with each step out. However, we have the problem of it never going to zero. It requires an infinite distance to go to zero. So there's a numerical relationship between these two diagrams, and you can see it right on the protractor. There's a numerical relationship between those two diagrams, so it should be possible to find a way, a method of calculation so that you can take an observation, pass it through this comparison, and thereby determine where the object is in space, and actually get predictable results that are accurate with what is perceived and what is measured. It's all there in these two diagrams. I've shown you the tools for you to use to develop your statement. I'll remind you that you said it isn't multiple heights, it's perspective, which is how they set the latitudes. And down here, you responded to Michael Dunleavy by saying that's because you took all of perspective out. So put it in, put the perspective in, and put numbers on it and show us how we can calculate an answer based on your approach. If you can show us the math, then maybe you could change people's minds. We have something that appears to work. You say it's wrong, but you're providing no alternate quantifiable solution. Unless you can show us a better quantifiable method, it is unreasonable to expect us to accept your statements as fact. You are a rational person. Clearly you can understand why it is unreasonable for us to accept your statements so long as you haven't provided a quantifiable solution. I'm asking you to show us the method. Can you do that? This is a challenge to Gary Wybenga to show us how to do it. Can you show us, Gary? If you can, please show us. If you can't, please tell us what you're going to do to determine your method. Thank you. This is FE Peer Review. If you enjoyed this video, please click the like button and all those other things. Have a great day. Bye-bye.